Okay, so today we're going to cover the rest of the water quality section, and but first I want to review, make sure everyone had a chance to get into the exam and take it. I saw that not everybody had done it, so if you didn't get into the exam and didn't get to take it, you got to come talk to me and we'll figure out what your situation is and how we can get you to take it, because we got to get everybody up to speed and on the same page, and then we should all be on the same pace. So the exam is at the end of Unit 1, right at the very bottom, but it closed on Sunday night, so I have to reopen it. If you have a reason that you weren't able to do it, we're being understanding and we'll get you in there and we'll give you another opportunity. So let me know if you didn't get a chance to take it. Okay, come see me after class, send me an email, let me know what's going on. So where we are now is Unit 2, which focuses on water quality. Last week we heard about several different water quality parameters and how to measure them, such as salinity and pH, conductivity, TDS, all that kind of stuff, alkalinity. And so we're going to review some of that as we go along today, but the main thing that we're going to focus on is nitrogen in aquaculture systems. So what is nitrogen? It's the elemental symbol for nitrogen. N, right? Nitrogen is the most abundant element in air, right? Makes up almost 78% of air, and that it occurs as N2. And you can have dissolved nitrogen gas in water that can cause issues, but most of the time when we're talking about the nitrogen that's in a fish tank or aquaculture system, it takes on other forms. There we go. So the feed, anything that a fish eats, is also comprised of a high percentage of nitrogen, right? Proteins have lots of nitrogen, and when that is broken down by the fish or not eaten by the fish, the fish converts it to ammonium, and there's a little bit that gets excreted through the waste, but most of it's excreted through the gills as a byproduct of consumption and digestion of the food particles. So ammonia and ammonium, right, we'll talk about those two different forms of ammonia, is the most basic first byproduct of eating from a fish. In a pond or the ocean or any natural body of water, as well as in your fish tank, what kind of organisms consume that? Bacteria, that's right. So there's different species of bacteria that specialize in different chemical forms. So we generalize and say all the ones that are eating ammonia or ammonium are Nitrosomonas species, and there's lots of different species, and some of the newer work that they have all these fancy genetic tools show that there's actually a pretty diverse group of bacteria, but for the purpose of this, we're going to call them Nitrosomonas are the bacteria that consume the ammonia. And it's an oxidation reaction, which means it adds oxygens, hydrogens go off, and we get nitrite, NO2. That gets consumed by another species of bacteria, the Nitrospira, or Nitrobacter, depending on whether you're freshwater or saltwater. And that's another oxidation reaction. It adds another oxygen to it, makes NO3, which is nitrate. So this is your typical nitrification process. That's the name of this process from here to here. And then nitrate is the form of nitrogen that's most available to plants. So if you add fertilizer to your lawn, it has your NPK ratio. Most of that nitrogen is is in the form of nitrate, and that's what's used in aquaponic systems. The nitrate's pulled out by a plant, or in submerged aquatic vegetation, will consume that nitrate and use it as a nutrient source. And then there's another set of reactions that happen in the sediments, which often happen below the area where there's oxygen, and you can get denitrification happening down there. So nitrification is happening in where there is oxygen, denitrification in the absence of oxygen. So we're going to break it down. Again, N2 is a gas. It can dissolve in water. You can have issues if you have a little like pinhole leak in your pump intake, okay? And then your pump is sucking that water through real fast. It's sucking air in and then becoming pressurized. You can get an excess of nitrogen gas dissolved in your water. And that can cause things like gas bubble disease and other, where you get like bubbles that can form under the skin or cause extra Popeye, stuff like that. So nitrogen itself can be a problem, but it's usually more of a mechanical issue than a biological issue. Again, the main byproduct of food is ammonia. And ammonia comes in two forms: ionized ammonia, right? An ion is not a balanced molecule. It has extra electrons or not enough electrons. If it has a plus sign, does it have extra electrons or not enough electrons?
If it has a plus sign, it has less electrons because electrons have a negative.
Right. Electrons have a negative charge. So this is missing an electron, gives it a positive charge. Or you can have unionized ammonia, which is NH3N. So there's another N sticking to it, because that's how the whole molecule is formed. But in general terms, we kind of drop that N off. And so we'll talk about ionized ammonia, unionized ammonia. When you do a test, you're measuring total ammonia. Typically, you can't differentiate between the two. And we'll talk about some of the ways that you can use some of the other water quality parameters to determine what percentage is unionized versus ionized. And then your nitrite, NO2, nitrate, NO3. So again, this is another diagram of the nitrogen cycle. Nitrogen that is in the food gets eaten by the fish or falls to the bottom of the tank, goes directly to ammonia, or is released as urine, feces, urea, or again, the highest percentage of that is as ammonia through the gills, and then goes through the nitrate, is either taken up by plants or kind of stays in solution as nitrates. So the two forms of ammonia: unionized ammonia, NH3, is toxic to fish or other aquatic life. Ionized ammonia is less toxic, does not have an impact. So we have to figure out which one is present. How much unionized ammonia is really the important thing when you're talking about are my fish going to die type of question. pH is the primary driver of that difference. Why would that be? What is pH measuring? It's acidity. And what's in solution to make acidity? I think you said it. There's a certain ion, thank you, in solution. H plus, hydrogen ion. So that is why we see that difference, is that the more hydrogen ions are in solution, is the pH higher or lower? More hydrogen ions.
More hydrogen ions equals more higher
higher acidity, which is what on the scale? Lower number, right? More hydrogen ions is more acidic, and which is lower on the pH scale. So, if there's more hydrogen ions in solution, there'll be more percentage of them will will be ionized ammonia. So low pH, more ionized ammonia. High pH, there's a lack of hydrogen ions in the water. It's an unbalanced thing, and it's stripping off those extra hydrogens and leaving it as a bare NH3 molecule. So let's talk more about this. Keep going to go that way. So what we see is that in this equilibrium, remember, just like we saw with the hydronium ion, hydrogen and hydroxide, OH, we get this back and forth where H and OH go together and make water, and that happens here as well, and it happens again as related to what is available as a pH. So this is kind of hard to read, but it's the table that you would use if you wanted to calculate what your unionized ammonia percentage was. And so it also changes with temperature. So temperature goes up, the percent ionized ammonia goes up, unionized ammonia, and pH goes up, and the percent goes up. And so here at a pH of 7, with a temperature of 16 degrees Celsius, you have 0.3% unionized. At pH of 10.2, at temperature of 32, it's 94%. So you get almost from 0 to 100%. But if you look at the sort of more range of relevant pHs, 8.4 or so would probably be the highest you'd see. At warm temperatures, you're up close to 20%. So still 20 times as much ammonia in the relevant range of pHs, or from 0.3 is actually 60 times. There are, calculators online that you can go to, type in all your water quality conditions, and it'll spit out your unionized ammonia. But that's really what you want to know. Like, you can do your little aquarium test and see bright green, say, oh my gosh, I have tons of ammonia, I'm in such big trouble. But if you're down here, most of it's not harmful to your fish. Those other water quality parameters might be harmful, but depending on what you have. But if you're talking about a freshwater fish that likes low pH, it's not really, getting impacted by that toxicity. Now you can see it better. It's just a bunch of numbers, but it's very much linear. Higher pH, higher temperatures, more toxic ammonia, more unionized ammonia. So if you see bright green and you're worried about it, how do I keep it from killing my fish? You could maintain a low pH. That's one way to do it. I had a student who graduated and he went to work on a tilapia farm, and he said they would measure the pH regularly, and it was always like 40, which is insanely high. But the pH was low, and tilapia are tough, and the fish grew, and we're pretty happy. So if you do a water change, you will remove that percentage of ammonia. There's some different chemical compounds you can add: Chloromex, Amquel, zeolite. You add them in there. Amolox, another one. They basically bind up the ammonia and remove it. Sometimes those are used during shipping and stuff like that. Or you can stop feeding, let sort of the filter catch up. So here's where it gets a little tricky, right? If we say the unionized ammonia over 1 part per million basically starts killing animals pretty quickly. But that's not what you see on your test, right? Your test is telling you total ammonia, only a portion of which is this toxic unionized. Again, different species have different levels of susceptibility to ammonia toxicity. These are some that are highly studied. They go from a salmon that are highly susceptible to shrimp and carp, which can handle pretty high levels of unionized ammonia. Okay. We have ammonia. How do we get from ammonia to nitrite? Bacteria. Which species? Nitrosomonas bacteria are going to oxidize the ammonia and turn it into nitrite, which is NO2 minus, another ion. And nitrite is sometimes a common killer in your aquarium startup because you do your cycling. Has anyone started to see nitrite show up in their filters or in their water quality tests? The ones that you started in there, added ammonia? Okay. All right. When you get in there, you'll probably you'll see some nitrite show up. And then once the nitrite goes away, people think, I'm good, I'm cycled, I'm all set. And usually there's a secondary nitrite spike that'll come up out of nowhere and kill your fish in a new tank. It is more powerful than unionized ammonia as far as the levels that are acceptable before it starts killing. Right? We saw like 0.1 or so 1 part per million of unionized ammonia was toxic. We're talking 0.05 of a nitrite can be toxic. Opposite of ammonia, lower pH makes nitrite more toxic. So this is again another equilibrium reaction. You got your OHs and the H's making water, so it's just how much of it is available as free molecules in the water, free ions in the water. And with the decrease in pH, you get more of the NO2 minus ion. So what they do in ponds or a lot of freshwater situations is if they see nitrite issues, they'll actually add salt to freshwater. Raising the salt level, releasing the chloride will mitigate some of that nitrite toxicity. From a fish health perspective, if there's high nitrite, it makes their blood turn brown. So one of the ways it kills is that it takes away the ability of the hemoglobin to absorb or carry oxygen, and it turns the blood kind of brown colored and kills animals. So again, adding salt, flushing it out, or increasing your beneficial nitrifying bacteria are all ways to reduce toxicity of nitrite. So again, different species have different levels, some on huge orders of magnitude from 0.2 to 0.4 all the way up to 160 to 200, depending on what they're living in. They're saltwater, freshwater, and what other kinds of conditions they're in. So nitrate is the third product in the nitrogen cycle, the third nitrogen form that we've talked about. And how does nitrate appear? What makes nitrate? The bacteria. The other species of bacteria was Nitrobacter. And nitrate is again an oxidation reaction, and this is not as toxic. So I've done a bunch of experiments on larval and juvenile fish measuring these LC50, which is same kind of things they do. We'd like to see how lethal a pesticide chemical is or anything like that. You expose them at lots of different levels and try to figure out at what level did half of them die. That's an LC50. Lethal concentration in the 50 is 50%. So when we would do this, basically for ammonia and nitrite, it would be pretty easy. For nitrate, sometimes it was hard to get enough in solution to kill the fish because it's just not as toxic. So we're usually talking about numbers in the thousands when we're talking about nitrate toxicity. So when students are doing all their water quality tests and they're like, my nitrate test is red, I say, so what? Because unless the only issues that you might, what issues might happen if you do have high nitrates? What other kinds of things might happen in your tank?
Algal growth.
Okay, you have food for the plant life, so you have algae blooms that can happen, and it can be harder to manage your tank from that perspective. But from a pure toxicity perspective, not that big a deal. Some crustaceans are a little more sensitive to nitrates, and corals and stuff like that are as well. But from a fish perspective, it's really not very toxic. Here's sort of that scale. Again, unionized ammonia, nitrite, and nitrate. You know, where's sort of the acceptable levels that are recommended. Again, nitrate's allowed to kind of build up there. All right. When we're going through this nitrogen cycle, these bacteria are what we call what is it called when they use oxygen?
Aerobic.
They are aerobic bacteria. Thank you. I just drew a total blank. So it's an aerobic reaction, and so when we look in our biofilters in here and we have all those little media pieces of plastic, they're usually rolling around with a whole lot of air because this reaction is using up oxygen. So when you kind of engineer a system, you have to first figure out, all right, how much oxygen are my animals, my fish, using up by swimming around and everything, and then, well, the bacteria are really going to use a lot of oxygen as well. You know, people who operate wastewater treatment plants or large fish farms think of themselves as bacteria farmers, because that's really what they're trying to cultivate, is some good bacteria that can do this reaction. So every time this oxidation happens, it uses, for each molecule of ammonia, 1.5 molecules of oxygen. For each molecule of nitrite, another 1.5 molecules of oxygen. And then, I think I have it over here. So your nitrous ammonius goes ammonia to nitrite, nitrobacter, nitrite to nitrate. And then there's another type of bacteria. So it's basically a whole other kind of system called a heterotrophic system, which doesn't use surface-dwelling bacteria of these two species, but it's a sort of a brown water system, like for those of you who went to the Biofloc farm where we harvested those shrimp, that's a heterotrophic system. And they metabolize the ammonia directly into nitrogen gas. But before we get there, we're just talking about, for all the purposes of your exam, we're talking about aerobic, sort of chemotrophic nitrification, which is the consumption of ammonia, converting it to nitrite, converting it to nitrate. So, those of you that are in lab, you started your little biofilter, right? You built it, cut a little hole in the plastic, you put the material in there. Why do you think that material was a good substance to use in your biofilter? Why was that media chosen? Those little balls. They look like golf balls, but
We've got a lot of surface area.
But they weren't solid on the outside. They have lots of little holes and crevices and surface area. So the more surface area you have, the more bacteria you can grow on it. And what you're trying to do is you're trying to create this graph with real-time data. Okay? So here's your concentration, how much is in concentration on the side. Here's your time. What you guys did was you went straight and just dosed it up to in here somewhere with ammonia. But if you just added fish and started feeding them, what you'd find is your ammonia would slowly go up. If you put more ammonia in the water, what do you think's going to start growing on your biofilter balls?
Microsomonas.
All right, you now have a food source. Bacteria being opportunistic little critters, they are going to be like, there's lots of food here. Let's reproduce like crazy and have lots of bacteria, and we'll all just sit around eating ammonia all day, and it'll be great. And so as these bacteria population grow as well, you start to see them eating that ammonia and creating nitrite. Now there's a bunch of nitrite in the water. Who's going to come along? Your nitrobacters are going to come along and be like, hey, this place is cool. There's tons of nitrite here, and I love eating nitrite. So they're going to start reproducing like crazy, and you're going to have real big high populations of nitrobacter, and their byproduct is going to be nitrate, and that is just going to sort of build up in the system. So as you get these real high populations of bacteria, it drives the ammonia back down to a stable point where it's very low because they're consuming it all. When you get your nitrobacter population going on, it drives that nitrite down to a low stable, or sorry, this is nitrite here, to a low stable. It takes a little bit longer. So again, this is like, you know, the ideal situation, and this is how it would always be, and this is the exact plot that you'll get when you guys do yours. But in reality, usually there are sometimes some secondary nitrite spikes and, you know, some ups and downs, and it's not all as smooth as that. But what you're doing by adding ammonia and just bubbling your filter in there with no fish is you're cycling your filter, or you're establishing bacteria populations so that when you do add fish, whatever waste they produce, there'll be bacteria there ready to consume it, and you won't have a buildup of anything toxic. Any questions about this? It's a little bit hard to see the different dots and stuff, but the first one is ammonia, second one nitrite, and the third one is nitrate. And as those bacteria populations get high enough, they drive that concentration down to nothing. In a typical aquarium, just with a regular filter on it, nothing else, the only way to get rid of the nitrate is just do your water changes. Drop the water, just exchange out and remove the nitrate that way. So the source of nitrogen, again, is coming from your feed. So if you're designing an aquaculture system and you know that your tanks are this big and you think you can have this density of fish, well, how much are they going to eat is going to give you the answer to how big of a filter do I need to consume all that nitrogen waste. So each kilogram of feed is about 3% ammonia. So for every kilogram of fish pellets you throw in there, about 0.03 kilograms of ammonium nitrogen are produced by fish. Once that is metabolized by the fish and the bacteria in there, you get some growth, you get carbon dioxide production, and you get nitrate. And then that biofilter consumes oxygen and alkalinity. So we talked a little bit about this last time. Alkalinity is the carbon source that they consume to at the same time that they're doing that oxidation of the nitrogen. So when we feed our striped bass system that's really highly densely populated, we throw, for every kilogram of food we throw in there, we throw 250 grams of baking soda, sodium bicarbonate, as a carbon source to keep that filter going, or else the alkalinity will drop. Those fish don't do well with low alkalinity, and eventually you'll crash your biofilter. And we lost a whole crop of striped bass 2 years ago to that is that the students were taking care of them. They were doing their whole thing and dosing them with bicarb every time they fed. And then over Christmas break, it was kind of just a hodgepodge of people coming in and just throwing food in there, and no one ever threw the bicarb in there. And eventually, the ammonia got really, really high, and a couple fish died, and because the biofilter crashed, and then they basically clogged up the dead fish clogged the pipe, overflowed the tank, and they all died.
The pH should have been coming down.
The pH was down a little bit, but it had gotten so high that it was a saltwater system, and the pH was high enough that we still had enough ammonia in there that.
So if at that point someone dumped some bicarb in after the ammonia was up, that could have been
That
a
could kill
real
them all.
disaster. That
Yes.
would have wiped out the whole tank.
So this is a test question I like to ask, is exactly that. Somebody does this whole scenario we just described where they feed their tank food, but they don't keep the alkalinity up. So what happens is the alkalinity is consumed, carbon dioxide is produced, pH goes down, ammonia goes up. Ammonia is super duper high, but all your fish are really are still alive because the pH is 7. They don't like the pH at 7. So you realize this happened. You do all your water quality tests, you're like, holy crap, I crashed my biofilter because my alkalinity is at 20. I better fix this. Take a big scoop of bicarb, you throw it in there, and what happens to the pH?
So,
pH goes up, which is what you want because your fish don't like the low pH. And what happens when the pH goes up? You go from ionized ammonia to unionized ammonia, from non-toxic ammonia to toxic ammonia, and all the fish die. So what should you do instead?
water change?
Water change until everything's kind of back to normal. But adding the dose of fixing the pH problem first will turn all that ammonia into unionized ammonia, which is toxic. Everybody follow me?
Will ionized ammonia go through regular nitrification?
The bacteria can consume both,
Okay.
but the bacteria can't consume it if they don't have a carbon source.
Okay, yeah.
So that's where that ammonia starts to build up, is when the alkalinity runs out. And you don't have, I think you have to maintain like a minimum alkalinity of about 80 or so to really have good biofiltration capacity. So, important things to remember: high pH, high temperature, higher percentage of unionized ammonia. Okay? Again, this is that percent scale, just shown a little differently. Still not easy to read from your perspective, totally get it. The nitrite spike that you often see is when your filter is sort of actively populating. You have lots of reproduction going on. You have the Nitrus simonis producing nitrite, and you have your Nitrobacter population increasing, and they're not all yet, like, they haven't filled all the little nooks and crannies and really populated all the surfaces. And they're not really long-lived little critters, so they're not super stable. And so what you can see is, again, these major fluctuations, and you can get that nitrite spike early on in your startup of an aquarium. So when people, again, kind of start it up, get it going, test it, as soon as they see that nitrite come down to 0, they're like, I got it, here we go, let's go spend $500 on brand new fish and put them all in the tank, and then not check it again for another 2 weeks, and then everything one day dies. All right, nitrate, again, not toxic compared to the other 2 forms of nitrogen, but it is very important for plant activity. So hydroponic systems, that's the nutrient that's taken up. Any kind of macroalgae production or anything that's got a plant-based component to it will remove some of that nitrate. But if you want to have a beautiful tank and you don't like scrubbing algae off the glass window of your tank, you probably want to remove those nitrates, because if you look in our reef tank in there, it looks pretty crappy right now because there's algae growing on everything. There's algae growing on all the rock, there's algae growing on the tank walls, and so you might want some sort of denitrification. Nitrification is ammonia, nitrite, nitrate. Denitrification is basically taking nitrite and nitrate and removing it from the water altogether as nitrogen gas. Okay? In natural systems, that typically happens in the sediments in areas with low to no oxygen. So it is called an anaerobic reaction. There's a lot of different ways to try to achieve this. It's always a challenge because oxygen is really important in your tank to keep your fish alive. So if you want to have another process that involves zero oxygen, you have to engineer a way to get all that oxygen out of there. So there's some, like we have these block filters where like the outer surface area that's facing the inside of the sump has nitrifying bacteria on it, and then there's sort of your parts that's against the bottom and against the wall that doesn't get really any flow that can generate these anoxic bacteria, anaerobic bacteria, and you can get some nitrogen removal. But again, focusing more on the nitrification process, that biofilter unit, you know, we just use our sumps and throw a bunch of media in there and make a biofilter out of it. What you need to consider is the pH, alkalinity, temperature, oxygen, salinity, and light that gets there can all impact the rate of biofiltration. So the bacteria can handle a pretty wide range in pH. For fresh water, the optimum range is in the mid-7s. For salt water, a little bit higher than that. Alkalinity, you need to maintain at above the sort of minimum rate to make sure that it's not a limiting factor for that nitrification. So you may have to add one of these buffers to increase the alkalinity. You know, we use sodium bicarbonate, not because it's the most powerful buffer, but maybe it's the safest one. You can't really overdose it. Some of these other ones, if you use soda ash, you have to use a lot less of it. But if you add too much, the pH can go way up to 9 or 10 and just kill stuff. So that's why we use this sort of rule of thumb here: 1/4 pound of baking soda per pound of feed, 1/4 kilo per kilo, and that maintains conditions that you can have good biofiltration. Temperature. At what temperatures would you likely see higher rates of nitrification?
Lower temperatures.
You think that they're more active at lower temperatures? Does everybody agree with him? You're talking about bacterial growth on food. Does your food spoil faster at warm temperatures or cool temperatures? So bacteria grows better at warm temperatures. I mean, they all have their optimum, and it can be too warm and stuff. But typically, higher temperatures, everything's a little bit more active, higher rates of nitrification. So basically, this is a really horrible sentence to try to get you to understand it. But if you're talking about a cool water fish, you have to have a bigger biofilter because the bacteria are not as active, so you need more of them. You need more surface area. Oxygen, we talked about that those bacteria are part of your whole calculation of the oxygen demand. You got to make sure that you can put enough oxygen in directly to that filter so that the oxygen does not go below 2 milligrams per liter, or else you'll start to kill off your bacteria. So that is something that is sometimes overlooked. If you just say, oh, I got media in there, everything's good. If it gets really, really high populations of bacteria and you feed it a lot, you need supplemental oxygen to help it out. Any questions about how all those things kind of go together? All right. Let's stop this right here.